Hello, welcome to the second lecture on P versus NP. I'm going to start off with a review of what we did in the last lecture because I got some feedback saying that I wasn't being clear enough in some parts. So let me go over a few things again. You may find the early parts a bit boring, I guess, if you're already okay with the previous video, but I think it's still good to listen in and then see if everything is okay with you. If you get everything, then that's fine. Also, remember that we do have a Q&A session every Tuesday. If something here doesn't make sense, please make a note of it and then bring it up during the Tuesday lecture and we can have a discussion. Because this topic does require a lot of explanation, so a lecture would be much better because you can ask me questions. Well, you can still do that during the workshop and during the Q&A session. So please do that if you have any problems. Now, the focus of this lecture is to talk about NP completeness and reduction. Maybe more on NP completeness, not so much on reduction because we're going to be doing that again in the next lecture. But if you don't get P versus NP, then obviously you're not going to get NP completeness either. So make sure you really understand the basic idea of P versus NP before we get there. So hopefully at the end of this lecture, you have a solid understanding of P versus NP, to the level that we need anyway. And I think that's good for a computing student to have a sound theoretical knowledge about P versus NP. Right, so let's get started. So in the last video, I discussed three classes. Well, four, I guess, if you count sub-PXP, but we kind of don't need it anymore, so you can ignore it from now on. We define what the class NP is, which is a set of problems that cannot be solved in polynomial time. But if you do have a possible solution to it, you can verify that it is correct in polynomial time. So this is the bit where someone got confused with what I said. So I'm going to talk about this definition again. But remember that the whole point of P versus NP is the question whether or not this class NP is a special class on its own. So like this picture you can see here, or if every single problem in NP is actually just a problem in P. And right now we have NP because we just don't know how to do them in polynomial time. So if eventually we know how to do every single one of them in polynomial time, we have NP equal to P, as pictured here. Now, this definition. Problems in NP are verifiable in polynomial time, but we don't know how to solve them in polynomial time. The question that I got was, how can you check if the solution is correct in polynomial time if you can't even produce a solution in polynomial time? Don't you have to produce a solution before you can check it? Well, I guess this is where I was unclear. What I meant here was that if you already have a solution, or I should say a possible solution, like someone gives you a possible solution to the problem, then all you need to do is to check whether or not the solution is correct. And you can do this in polynomial time if the problem is in NP. Well, that's the definition. So it's not like you have to create a solution and then check it, because that will obviously take more than polynomial time. So hopefully that's clear now. So you already have a solution and you're only checking if it's correct or not, and this can be done in polynomial time. Making the solution, yes, that will cost more than polynomial time. So in short, P is easy to check, easy to solve. We know P, we love P, polynomial time, right? We've done a lot of P stuff. NP is easy to check, but it's hard to solve. Or is it? Well, that's the thing. Maybe NP is also easy to solve, and that makes P equal to NP. That is what we want to do. We want to know whether or not NP is special. Or maybe another way to say it is like, does NP actually exist? What do I mean by that? Imagine that there aren't that many problems in the world. So there's only a bunch of them represented by these dots, and some of them are in NP. So one more time, you don't know how to solve them in polynomial time, but you can verify if a solution is correct in polynomial time. And let's say that I picked this problem and worked out that, oh, I can solve you in polynomial time. Great. So I move it under P. And well, actually, I can solve all of these in P. So I can move all of them out of P as well. Well, what does that mean? That means that there's nothing special about this NP. NP is just P. Or like NP doesn't actually exist. Alternatively, if we can prove that we can't do some of these problems in polynomial time, well, that means this NP class is indeed special. Why? Well, we can verify the correctness of these problems in polynomial time. We can't do it on these ones. We can definitely do it on these ones, on P, right? But these ones, we can verify the correctness in polynomial time. So that we can't do it in polynomial time. We can't solve it in polynomial time. So cool, there's a new class of problems called NP. You see, right now, we're not even sure that NP is a thing. Maybe it doesn't exist. Maybe it does exist. That is the million-dollar question. Okay, so hopefully it's clear what we're trying to achieve here. We're trying to show that P is NP, or that P is not equal to NP, one or the other. And we're going to talk more about how we can achieve that. In particular, we're going to talk about what people have done to try to prove that P is equal to NP, or if P is not equal to NP. Now, I mentioned that in order to do this, you have to prove that every single problem in NP is also NP, which is a very hard thing to do, right? Because you have to look at every single problem there is. But we do have something called NP completeness, which is going to make this easier. So you don't have to prove every single problem. But first, we have to talk about NP hard. And before we can talk about NP hard, we have to talk about decision problems and optimization problems. So it's going to be a while before we get there. And we're going to start with decision problems and optimization problem first. So you have seen these in, I think, week 1. And you kind of know what they are anyway before you start this unit. In optimization problems, you have to find the optimum value. So something like, what is the weight of the longest path from A to B? What is the weight of the shortest path from A to B? Go find the Hamiltonian cycle. We talked about these problems in the previous lecture, so hopefully you remember what Hamiltonian cycle is. It's a cycle where you visit every vertex once. Whereas the decision problem is like the weight of the longest path. Is it less than K? Is it more than K? This graph, does it have a Hamiltonian cycle? So it's a problem where the only output is just yes or no. One of the two. So which one do you think is harder? Well, it depends, right? But here's one example, the Euler cycle, which you did in Completeness 5. But with the optimization version of the Euler cycle, you have to actually find the Euler cycle. So Euler cycle is a cycle where you use every single edge. You start from one vertex, you use every single vertex, and every single edge, and you go back to the original vertex. So there are algorithms to do it. The basic one is called Fleury's algorithm. It's pretty simple. You can look it up if you're interested. But the decision problem is very, very easy. If I just ask, is there an Euler cycle in the graph? Then you just go through every single vertex and you make sure that every single vertex has an even degree. Because if you have an even degree, you can come in and you can come out again. So that is a necessary condition. So in general, yes, the decision problem is easier. So why does this matter in the whole P versus NP discussion? Because you can cast an optimization problem into a decision problem. That is, you can use an algorithm for the decision problem to find a solution to the optimization problem. Like how? Well, if you look at the shortest path problem, the optimization problem wants to know the weight of the shortest path, right? Whereas the decision problem just wants to know if the weight is less than K, say. So here's the trick. Just keep on applying the decision problem. Ask, is the weight of the shortest path less than 0? Yeah? No? No? Well, if it's no, then I'm going to ask another question. is the weight of the shortest path less than 1? Yes, no, no. Is the weight of the shortest path less than 2? Yes. Oh, if it's yes, then I know that the weight of the shortest path is 2. I just found the answer to the optimization problem. And this is important because if I can solve the decision problem in polynomial time, I can also solve the optimization problem in polynomial time. Because what do? We ask if the weight is 0, then if it's 1, if it's 2, and eventually we'll hit the right number, right? Because we keep on going up. So how many times do I have to do this? Well, the shortest path has at most phi minus 1 edges, right? So if I have to ask this at most phi times w, where w is the largest weight in the graph. So it's constant time phi. That's how many times I have to do it. In other words, if I have a polynomial time algorithm to solve the shortest path decision problem, then I also have a polynomial time algorithm to solve the shortest path optimization problem. So what is the moral of the story here? Well, it's this. Can the decision problem be harder than the optimization problem? Well, in decision problems, you only need to say yes or no. In optimization problem, you have to do something. You have to find the answer. You have to find the thing that will give you yes or no. So optimization problem is at least as hard as the decision problem, meaning you can't have the optimization problem easier than the decision problem. But can the decision problem be as hard as the optimization problem? And the answer is sure. Look at Hamiltonian cycle. The optimization problem is going to say, go find the Hamiltonian cycle. Okay, cool. What about the decision problem? Is there a Hamiltonian cycle? Well, if there's one, you got to find it anyway, right? There's no easy way to check it. So yeah, in this case, the decision problem is just as hard as the optimization problem. How is this relevant to the P versus NP problem? Well, if you have an NP problem, you can use your solution to the decision version of the problem to work out the solution to the optimization version. Okay, there's a big if that we're going to discuss later. But for now, remember that we want to know if we can solve the NP problems in polynomial time. So if I can solve the decision problem in polynomial time, I can convert that into an optimization problem, also in polynomial time, in the way that you've seen earlier. So that means I can solve the optimization version in polynomial time. Like, here's a summary of what can happen. You can have your decision problem in P. That means the optimization problem will also be in P. Or if your decision problem is not in P, then you also know that your optimization problem is not in P, because the optimization problem can't be easier than the decision problem. Now, this is something we have to discuss later. We can have the case where the decision problem is in P, but the optimization problem is not in P. Yeah, we'll talk about that later. And finally, this one just can't happen, because again, the optimization version can't be easier than the decision version. So basically, when it comes to NP problems, you can just focus on the decision problems, because they will lead to the solution to the optimization problem. Now, this is where we have to discuss that big if that I mentioned earlier. I'm gonna call this the gray area because it's gonna make your hair turn gray. All right, what is an optimization problem? For example, the longest path problem. What do I mean by optimization problem? Are you gonna ask the weight of the longest path from vertex A to vertex B? Or are you actually gonna ask me to find the set of the edges that make the longest path from A to B, right? Do you just need the weight, or do you also need the edges? So some may argue that the second problem is a search problem, not an optimization problem. So why does this matter? Well, because you see with the second definition, the decision version of the longest path can't be used to solve the optimization problem, right? If I just ask, what is the weight of the longest path? What is the weight of the longest path? You don't actually know the set of edges. So it's like we have two different definitions of optimization problem. Like the first one, just find the optimum value. The second one, well, give me the combination of elements. Like give me the things that will give me the optimum value as well. Again, I said we can argue that this is actually a search problem. But nevertheless, whenever you encounter an NP problem, you may hear this. You may, people would just say, traffic salesman, go find the cheapest route from town A to town, back to town A, sorry, that goes through every single town, right? They're just gonna say cheapest route. When you say cheapest route, is that just the cost of the route? Or do you also want the route? Because if you also want the route, then it's not NP. Why? Because I can't verify if a route is actually the shortest route. Well, I can't do it in a moment in time. And actually working out if the route that you give me is the cheapest route is the same effort as finding the cheapest route itself. So the decision version is not going to help with the optimization version. Now, in CLRS, if you have been reading it, it uses the first definition. That's also what I did with the graph stuff. If you remember, with the shortest path, I don't actually need the path. I just want the weight of the shortest path. But what I see in CLRS is this. When we're talking about P versus NP, even a decision problem is hard anyway. As in, I can't do it in P. So if we can't do the decision problem in P, it doesn't matter if you can't use it to solve the optimization problem, like no matter how you define it. No, it's going to be hard anyway. And of course, if you use the second definition, then what I said earlier was wrong, because you can't use the decision version to solve the optimization version, or at least sometimes you can't. And it's obvious with the longest path problem, right? Because you simply won't get the path. But does it matter? To me, no. And I kind of agree with CLRS here. I think P is not NP. So I'm pretty sure it doesn't matter because the decision problem is hard anyway, and it's not going to help me solve the optimization problem efficiently. I also think that if you solve the optimization problem, you have to do the search problem anyway, as in, I don't think you can get the optimum value unless you go look for them, like unless you look at the elements, at least for the NP problems that I've seen. So this means I can't agree with the second definition. So why mention all this? It's going to come up when we discuss NP hard, and I guess NP complete as a consequence. So this is something for you to keep in mind. For now, I think you can just use the second definition if you feel this is more natural to you. It's not really going to matter because I'm not going to examine you on this. This is purely for your understanding, and also not saying that one is right over the other. I'm just saying that out there, people don't agree on definitions sometimes. And to really understand this, you have to do a lot of complexity theory because we have a lot more definition to handle these kind of things. So yeah, we're not going to go that deep. So this is the best I can do. Okay, I think I'm going to stop here. That's not the end of the slides, but we're getting close to 20 minutes, or maybe already past that. And we talked about a lot of stuff already, so we still have a bit to go, and I don't want to make this video too long. So I think this is a good point for a break. I'm going to cut it here, and I'll just continue with NP hard in the next video. So make sure you understand this stuff before you go to the next video though, okay? All right, I'll see you soon.